let's use this idea of making a guess with undetermined coefficients to solve some more non-homogeneous linear differential equations with constant coefficients. So here's an example, y double prime plus 9y equals e to the minus 4x. So let's find a general solution for this. We know we're going to need the complementary solution, so let's just find that right away. We're going to find complementary solution. So the associated homogeneous equation is y double prime plus 9y equals 0. The characteristic equation for this is m squared plus 9 equals 0. Solving this for m gives plus or minus 3i. And so our complementary solution will be, because this is purely imaginary, our complementary solution will be a combination of sines and cosines. So some constant times sine of 3x plus some other constant times cosine of 3x. Okay, so now all we need to do to get a general solution is find a particular solution to the non-homogeneous equation. And we need to make a good guess for what sort of function we might get. Well, the right-hand side of this differential equation, the non-homogeneous term over here, it's an exponential this time. So what we need to think about is if we plug our particular solution guess into this differential equation, right, we start taking combinations of derivatives of our guess. What would we have to guess for combinations of derivatives to give us an exponential? So what sort of functions has exponentials as its derivative? Well, exponentials. So we need an exponential, probably with an undetermined coefficient. But what should the, right, probably we need e to some power here. Seems like there should be an x. But what coefficient should be in here? Is that undetermined? Well, if we start taking derivatives of an exponential like this, the coefficient in the exponent never actually changes. So if we want to end up with a coefficient of minus 4 in this exponent, it had better start out being minus 4. So this one actually isn't undetermined. That's a minus 4. But this coefficient in front might be anything. So that's our undetermined coefficient in this case. Now that we have made a guess that we think might work as a particular solution, we can start taking derivatives to plug our guess into the differential equation. So take one derivative, y sub p prime is minus 4 times capital A e to the minus 4x. Take a second derivative, y sub p double prime is 16a e to the minus 4x. Plug all this into the original differential equation. So 16a e to the minus 4x plus 9 times y. So y sub p is a times e to the minus 4x. And this is supposed to be equal to e to the minus 4x. Now combining terms on the left, it looks like we get 25 times a e to the minus 4x equals e to the minus 4x. Now we can multiply both sides by e to the 4x to get rid of the e to the minus 4x. We get 25a equals 1, and so a is 1 over 25. And now we know our particular solution. Our particular solution is 1 over 25 e to the minus 4x, and we can write our general solution. Our general solution is the particular solution, 1 over 25 e to the minus 4x, plus the complementary solution, which was c1 times sine of, is it 3? Yes, 3x, plus c2 times cosine of 3x. Okay, so for this particular example, our inhomogeneous term on the right-hand side of the equation was an exponential, and the guess we made was an undetermined coefficient in front of that exponential. All right, let's look at another example. What if our inhomogeneous term is a trig function? So in this case, it's sine. it works out similarly if you have some multiple of a cosine function on the right-hand side here. So let's see what happens. As usual, let's find a complementary solution first. So the associated homogeneous equation is y double prime minus 4y prime plus 4y equals 0. This has characteristic equation m squared minus 4m plus 4 equals 0. This factors. This one's a perfect square. It's m minus 2 squared. And that means our complementary solution is going to be some constant times e to the, so I guess I should say m is 2. So this is the repeated root case. So our complementary solution is some constant times e to the 2x plus some constant times x e to the 2x. Remember, when you have a repeated root, that's when you get the exponential that you think you should get, and also x times that. Okay, so now we can find a particular solution. And for undetermined coefficients, right, it all comes down to making a good guess. So what sorts of functions, when you start taking derivatives of them, what sorts of functions produce sines? Well, if you started with cosine, you would get sines coming out of your derivatives. But also, if you started with sine, you could get sine to show up in your derivatives because the second derivative would also have sine. So it looks like we actually need two terms here. Taking derivatives doesn't change what's inside the trig function. So if we want x to show up inside, we should probably start with x inside. But the coefficients in front, as you start taking derivatives, might change, and so we need some undetermined coefficients. So how about a cosine x plus b sine x? Now that we have a guess that we think might work, we need to start taking derivatives. So y sub p prime is minus a sine x plus b cosine x. Y sub p double prime is minus a cosine x minus b sine x. And now we have to plug all of this into the original differential equation, which is going to be a bit of a mess. So let's see, y sub p double prime. So that's minus a cosine x minus b sine x minus 4 times y prime, and y prime is minus a sine x plus b cosine x plus 4 times y, and y is a cosine x plus b sine x. And this is all supposed to be equal to sine x. Okay, so if we're going to compare this whole left-hand side to sine x, then probably we should gather up all the sine terms and gather up all the cosine terms. So let's see, our sine terms are, let's see, we have a minus b right here. We have a plus 4a right there. And we have a plus 4b right here. Okay, for our cosine x terms, we have, let's see, right here is a minus a, and then here's a minus 4b, and here's a plus 4a. And this is all supposed to be equal to sine x. So combining the stuff in parentheses here, so that's going to be 3b plus 4a, and it's that times sine x. And then looking at our cosines, we have, looks like 3a minus 4b, and that's all times cosine x. And this is supposed to be equal to sine x. All right, well, if these are supposed to be equal for every value of x, that means this coefficient here must be equal to this coefficient over here, which is 1, and the coefficient on cosine here, 3a minus 4b, must be equal to the coefficient on cosine on the right-hand side. And there isn't a cosine on the right-hand side, but that just means the coefficient in front of cosine is 0. So again, we get some equations that are going to let us find the undetermined coefficients. So the first one that I've underlined in red here is 3b plus 4a equals 1. And the other one is 3a minus 4b equals 0. Okay, when you do undetermined coefficients like this, it turns out the system of equations that you get for your undetermined coefficients is always a linear system of equations, and so it's always possible to solve it. So let's solve this system. You can use any trick you want for solving the system of equations. It looks like for this system, it's going to be easiest to maybe use substitution. So let's solve this equation for a. Let's see, move the b's over, divide by 3. So a is 4/3 b. And then put that into the other equation. So 3b plus 4 times 4/3 b equals 1. So 3b plus 16/3 b equals 1. So 3b is 9/3. 9/3 plus 16/3, 25/3. b equals 1. And so b is 3/25. And now we can go back and find a. Oops. Right, a is 4/3 b, so a is 4/3 times b, which is 3/25. So this is 4/25. And now we know our particular solution. Our particular solution is, let's see, I put the cosine first, I think. Yes, a times cosine, so 4/25 times cosine x plus b times sine x, so 3/25 times sine x. And so the general solution to the original differential equation is the particular solution, 4/25 cosine x plus 3/25 sine x, plus the complementary solution, which is some constant times e to the, what was it, 2x, plus some other constant times x e to the 2x. Okay. So as we're doing these examples, we haven't been checking that the particular solution we find is actually a solution to the original differential equation, but it is a good idea to check if you have time, or if you doubt your result at all. You can always just take the particular solution you find and actually plug it into the original differential equation.